We'll now consider what it means if a characteristic polynomial has two complex solutions. First, we'll emphasize that if there is a complex solution, there are two of them. They appear in conjugate pairs, a plus bi and a minus bi. In a sense, we don't need to do anything special. We get solutions as expected. However, we will not write solutions in a way that involves complex exponentiation. Suppose we're looking at a differential equation ay double prime plus by prime plus cy equals 0. Now suppose that the characteristic equation ax squared plus bx plus c equals 0 has complex roots a plus bi and a minus bi. These give us solutions e to the a plus bi t and e to the negative bit. These are linearly independent and give us this general solution. Y equals d sub 1 times e to the power of a plus bi times t plus d sub 2 times e to the a minus bi times t. However, we do not write our solution like this. Instead, we use Euler's formula to rewrite this. And Euler's formula, if you haven't seen it before, says that e to the power of it is the cosine of t plus I times the sine of t. So we'll first break these apart. D sub 1 e to the a t e to the bi t plus d sub 2 e to the a t e to the negative bit. Then use this formula to rewrite this and this. Y equals d1 e to the a t times the cosine of b t plus I sine of b t plus d2 e to the at, the cosine of negative bt plus I times sine negative bt. We'll pull out these e to the at's here and here. Y equals e to the at times d1 cosine bt plus d1I, the sine of bt, plus d2, the cosine of negative bt, plus, missing an I there, plus d2 I, the sine of negative b times t. Now, the cosine is even and the sine is odd. So the cosine of negative bt is the cosine of positive bt, and the sine of negative bt is negative the sine of t. So y equals e to the at d1, the cosine of bt, plus d1I, the sine of bt, plus d2, the cosine of bt, minus d2I times the sine of bt. And now we'll group the cosines and the sines. Y equals e to the at times d1 plus d2, the cosine of bt, plus d1 minus d2 I times the sine of bt. You can probably predict that we'll write this sum as a single term. C1 equals d1 plus d2. Maybe a little surprisingly, over here we'll include the imaginary unit in the constant. C2 equals I times D1 minus D2. So finally, y equals e to the AT C1 the cosine of BT plus C2 the sine of BT. And this is the general solution. Note that if we allow D1 and D2 to be real or complex, this could be purely real. For example, if D1 equals I and D2 equals negative I, then y equals e to the AT times negative 2 sine BT. So it's possible to get purely real solutions, even though we had this imaginary unit floating around. In this video, we've considered what happens if a characteristic equation has complex roots. We see that although the imaginary unit I appears, the ultimate solution to the corresponding differential equation is, or can be assumed to be, entirely real.